4.5 billion years ago, there is no Earth yet. There is no sun blazing at the centre of our solar system, no familiar planets tracing their well-worn elliptical paths through the void, no moon to pull tides across oceans that do not exist. There is only the solar nebula, a vast, rotating disk of dust and gas that stretches beyond the furthest reaches of human imagination, spinning with the leisurely, hypnotic grace of deep time itself in the cold vacuum where our entire solar system will eventually find its home. This nebular disk extends outward for billions of kilometres, a gossamer-thin collection of matter so diffuse that most of it qualifies as empty space, yet containing within its gentle spiral arms all the raw materials that will someday compose planets and moons and asteroid belts and the countless smaller bodies that populate interplanetary space. The temperature here hovers perpetually near absolute zero, that theoretical point where atomic motion nearly ceases entirely and molecules slow their eternal dance to something approaching stillness. In this profound cold, particles of silicon drift alongside specks of iron. Fragments of magnesium mingle with dust grains of aluminum, calcium, nickel, and countless other elements that will someday compose mountain ranges and ocean floors, and the iron cores of worlds. Each individual grain measures smaller than anything the human eye could ever perceive, smaller than bacteria, smaller than the wavelength of visible light itself, yet each carries within its atomic structure the potential for continents. They move through this cosmic medium with the infinite patience that only geological time can teach, following orbital paths so vast and so gradually curved that their motion appears almost linear, like snow falling through air so still it might as well be solid. Occasionally, after drifting for centuries without contact, two particles bump into one another with touches so gentle they barely register as physical interaction. The collision happens at velocities measured in mere centimetres per second, slower than the growth of fingernails, gentler than the settling of dust on a windowsill. Sometimes, through forces so weak they hardly qualify as bonds, these microscopic fragments somehow manage to stick together. The process unfolds with a slowness that makes glaciers seem hurried, makes erosion appear violent, makes the growth of mountains look like sudden eruptions. Each successful connection between particles represents not moments or hours or even years, but thousands upon thousands of years of cosmic choreography, of orbital mechanics playing out across scales that dwarf human comprehension. Individual dust grains take millennia to find their partners in this vast, cold dance, and when they finally do encounter one another through the patient working of gravity and chance, they form clusters no larger than the pebbles a child might collect along a beach, though these pebbles exist without beaches, without oceans, without ground of any kind, suspended in the weightless drift of interplanetary space, turning end over end in orbits governed by laws written in the most fundamental language the universe knows, the mathematics of gravity and momentum and angular momentum conservation. Scientists have given this process the technical name accretion, though the word carries connotations of urgency and accumulation that feel almost violently inappropriate for something that unfolds with such extraordinary, almost meditative leisure. These cosmic pebbles, having invested thousands of years in their own formation, now spend tens of thousands more in the patient work of gathering their neighbours into collections the size of rocks. The rocks, in turn, dedicate millions of years to the gradual accumulation of partners, slowly building into boulders that tumble through space like ancient, silent sculptures. The boulders eventually grow into objects approaching the size of mountains, though mountains that exist without any context except the endless black of space and the distant, cold light of stars still condensing from their own nebular material in regions of the galaxy far from this particular stellar nursery. The scientific mystery that lingers here, patient as the accretion process itself, involves the precise mechanism by which these infinitesimal particles manage to overcome their natural tendency to bounce apart when they collide. The physics of the situation suggest that impacts between dust grains should result in fragmentation rather than aggregation, yet somehow aggregation wins out often enough to build worlds. Current theoretical models propose that static electricity might play a crucial role. The same electrostatic force that makes hair stand up after rubbing a balloon or causes socks to cling together in a dryer. Though operating here on scales both vastly larger and impossibly smaller than human daily experience. Perhaps the van der Waals force contributes significantly that whisper-weak attraction between molecules that becomes noticeable only when surfaces approach each other very closely, somehow managing to hold cosmic dust together just long enough for gravity to gradually take over the work of assembly. But no human being has ever directly observed this fundamental process happening. No laboratory on Earth can perfectly replicate the precise environmental conditions of the primordial solar nebula, with its specific temperature gradients and pressure variations and electromagnetic field configurations and radiation levels, and the countless other variables that influence how matter behaves in such extreme conditions. So this most essential step in planetary formation, the critical moment when scattered matter first decides to abandon its individual existence and begin the collaborative work of becoming a world, remains beautifully, mysteriously, quietly uncertain, like a fundamental question written in a language we can almost but not quite translate. The ironies embedded in this process settle here in layers, like sediment accumulating on an ocean floor that will not exist for hundreds of millions of years yet. The sequence of events that will eventually create the most geologically dynamic, tectonically active, volcanically restless planet in the known solar system begins in conditions of nearly perfect stillness, where movement happens so slowly that entire mountain ranges could rise and fall on modern Earth in the time it takes a single dust grain to drift from one side of the forming solar system to the other. The forces that will someday drive continental plates across Earth's surface with enough accumulated power to raise the Himalayas and split the Atlantic Ocean and reshape the entire geography of continents start here as interactions so delicate, so gentle, that they could be disrupted by disturbances too small to measure with any instrument humans have yet devised. The world that will eventually teem with billions of different species of life, from the smallest bacteria to blue whales, from redwood trees to microscopic plankton, begins its existence as completely sterile dust suspended in a void so profoundly empty that individual particles can drift for centuries, sometimes for millennia, without encountering so much as a single neighbour. The planet that will develop weather systems and ocean currents and atmospheric dynamics complex enough to sustain life begins as matter so cold and still that it makes the vacuum of space seem bustling with activity. Here, in this pre-planetary quiet that stretches across geological epochs, time moves like honey cooling a winter that promises never to end. 1,000,000 years passes a temporal span that encompasses the entirety of recorded human history dozens of times over. That includes the rise and fall of civilizations, the evolution of species, the formation and erosion of landscapes, and the largest objects in what will someday become Earth's immediate cosmic neighborhood are perhaps the size of the asteroids that occasionally streak across our modern sky. Irregular chunks of rock and metal tumbling through space in eccentric, unpredictable orbits that very occasionally, through the patient working of celestial mechanics, cross paths with their neighbours, when these protoplanetary fragments do finally meet after eons of separate wandering, the collisions happen at velocities that would instantly vaporize any rock existing on today's Earth, speeds measured in kilometers per second that would turn granite into plasma and iron into expanding clouds of gas. Yet somehow, impossibly, through mechanisms that planetary scientists continue to debate in academic conferences and research papers, these violent encounters sometimes result not in mutual destruction, but in gentle merger, as if the universe has not yet learned the devastating art of catastrophic impact, as if matter itself is still practicing the fundamental skills of becoming solid and remaining that way despite the forces trying to tear it apart. The ambient temperature of the space surrounding this slow-motion construction project holds steady at approximately minus 270 degrees Celsius, a cold so profound and absolute that it approaches the theoretical limits of coldness itself, that point where atomic motion slows to almost nothing and the fundamental particles that comprise all matter hover on the edge of complete stillness. At such temperatures, nearly every substance that humans have ever encountered in their brief terrestrial experience would exist only as frozen crystals, brittle and lifeless as ancient ice preserved in polar glaciers that have never known the touch of sunlight. Carbon dioxide, which flows invisibly through Earth's modern atmosphere and sustains the photosynthetic processes that feed all plant life, becomes solid snow that would shatter like the most delicate glass at the slightest touch. Water, that most essential medium of all life as we know it, the substance that comprises the majority of every living cell, transforms into a material harder than the steel used to construct the tallest skyscrapers and longest bridges. Even helium, that most reluctant of elements to condense under any circumstances, that noble gas which resists chemical bonding with the stubborn independence that characterizes its entire family in the periodic table, begins to consider the remote possibility of becoming liquid under such extreme conditions, though it maintains its resistance with the determined aloofness that has made it useful for filling balloons precisely because of its refusal to react with anything. Hydrogen, the most abundant element in the universe and the primary constituent of the stellar material slowly condensing into what will become our Sun, exists here as a solid so hard it could serve as construction material. If there were anyone present to construct anything, if there were any purpose for construction in this realm where matter follows only the patient laws of physics, yet within this cosmic deep freeze, buried in this realm of absolute cold that makes the most severe Antarctic winter seem tropical by comparison, the seeds of what will become the most molten, volcanic, geologically restless world in the solar system are slowly, methodically, grain by grain, taking their first tentative shape. The irony writes itself across the void in letters too large to read, except from the perspective of deep time, in a script composed of orbital mechanics and gravitational interactions that will not be decoded by conscious minds for billions of years. The planet that will someday feature surface temperatures hot enough to melt lead and vaporize zinc begins its formation in conditions cold enough to freeze the very atmosphere that terrestrial life will someday breathe. As millions of years accumulate like dust settling on a cosmic windowsill that spans the breadth of the inner solar system, the largest aggregations of matter in this region of space grow steadily from pebble size to boulder size to mountain size. Though these familiar designations carry little meaning in an environment without gravity strong enough to define concepts like up and down, without atmosphere to provide the resistance and friction that make motion feel substantial, without any of the familiar reference points that allow human perception to make sense of scale and distance and relative size. These protoplanetary bodies tumble through the vacuum in complex, overlapping orbits that follow the mathematical laws of celestial mechanics with the perfect precision that characterizes all natural phenomena, yet appear random and chaotic to any hypothetical observer attempting to predict where any particular object will be located at any given moment in the far future. The scientific mystery deepens and becomes more intriguing as these objects grow larger and their gravitational influence begins to extend farther into the surrounding space, creating zones of influence that reach well beyond their physical boundaries. Current theoretical models suggest that once a protoplanetary body reaches approximately 1 kilometer in diameter, roughly the size of a large asteroid in today's solar system, its gravitational field becomes strong enough to significantly influence the motion of nearby dust particles and smaller objects, creating what planetary scientists call gravitational focusing. The remarkable ability to collect material from a much larger area of space than the object's physical cross-section would normally allow through simple geometric collision probability. This represents a crucial threshold in planetary formation, a tipping point where the character of growth transitions from the painfully slow process of direct collision, which depends entirely on the chance encounter of objects following intersecting orbital paths, to the more efficient mechanism of gravitational accumulation, where the growing protoplanet begins to actively influence its environment and gather material from an ever-widening sphere of influence. Yet the precise details of this transition, the exact mechanisms by which gravitational focusing operates under the specific conditions of the early solar system, remain frustratingly unclear to modern planetary science. Hidden in the complex mathematical interplay between gravity, orbital mechanics, collision dynamics, and the physical properties of primitive solar system materials that no laboratory on Earth can perfectly replicate. The process that emerges from these conditions resembles nothing so much as a cosmic game of gravitational billiards played in extreme slow motion across millions of years, with rules that become more complex as the players grow larger and their gravitational influence extends farther into space. Objects that began their existence as individual dust grains smaller than bacteria, then became pebbles no larger than marbles, then rocks the size of boulders, now exist as irregular chunks of loosely consolidated material ranging from structures comparable to city blocks to formations approaching the size of small mountains, though mountains that exist without peaks or valleys, without weather to erode them, without any of the familiar geological processes that shape terrestrial landscapes. They follow elliptical orbits around the gravitational center, where the sun is slowly condensing from its own vast collection of nebular material, occasionally intersecting with the orbital paths of their neighbors in encounters that occur perhaps once every few thousand years, meetings that has been mathematically inevitable since the moment their orbits were established by the initial conditions of the solar nebula's collapse. When these cosmic appointments finally arrive, they represent collisions between objects that have been building toward this singular moment for geological ages, encounters freighted with the accumulated potential energy of eons. The proto-Earth grows through these encounters like a snowball rolling downhill. If the hill were the size of the solar system and the rolling took millions of years, each successful merger adding not just mass but angular momentum, kinetic energy converted to heat, an increasingly complex internal structure that reflects the varied composition of the impacting bodies. The early collisions between relatively small objects moving at modest velocities might result in gentle accretion, with the smaller body simply adhering to the larger one like a cosmic snowball gathering more snow. the impact energy insufficient to cause significant heating or structural disruption, but as the objects grow larger and their mutual gravitational attraction increases, and as gravitational focusing causes more distant objects to be drawn into collision courses, the relative velocities at impact begin to increase dramatically. These encounters release energy measured in the same units used to describe nuclear explosions, though the energy dissipates over much longer timescales and much larger volumes of space. The accumulated heat from these increasingly violent collisions begins to warm the growing protoplanet, marking a fundamental transition in its character from a cold aggregation of cosmic debris to something approaching a warm, perhaps even hot, celestial body whose internal temperature reflects the violence of its formation. The iron and nickel within the consolidated material, originally frozen solid as interstellar ice in the cold depths of the solar nebula, begins to soften under the accumulated thermal energy of countless impacts, each collision adding to a heat budget that grows larger with every passing millennium. Lighter materials, particularly those containing significant amounts of water ice and frozen carbon dioxide that were incorporated during the early stages of accretion, start to sublime directly from solid to vapor without passing through the intermediate liquid phase, creating the first thin wisps of what might generously be called an atmosphere, though one so tenuous and ephemeral that it barely qualifies as gas rather than a slightly elevated vacuum decorated with occasional molecules. This primitive atmosphere bears no resemblance to the oxygen-rich envelope that will someday sustain complex life, nor even to the carbon dioxide-dominated atmospheres that characterize Venus and early Mars. Instead, it consists primarily of water vapor and carbon dioxide escaping from the warming surface materials, along with traces of methane, ammonia, and other simple compounds that represent the chemical inventory of the original nebula materials. The atmospheric pressure measures so low that any liquid water, should any manage to form, would immediately boil away into space, regardless of temperature, a physical impossibility that will persist until the growing planet accumulates enough mass to generate gravitational fields strong enough to retain a substantial gaseous envelope. The mathematical beauty of orbital mechanics ensures that not all collisions between protoplanetary objects result in successful accretion and growth. Some encounters occur at velocities too high for the gravitational binding energy of the objects to overcome their kinetic energy of approach, resulting instead in catastrophic fragmentation that sends debris flying in all directions across the solar system. These hit-and-run collisions follow the same physical laws that govern successful mergers, yet produce dramatically different outcomes depending on subtle variations in approach angle, impact velocity, and the internal structure of the colliding bodies. The fragments created by these destructive encounters follow complex trajectories determined by the vector sum of their original orbital motion and the impulse imparted by the collision. Some pieces travel at velocities that carry them beyond the gravitational influence of the proto-Earth entirely, destined to wander the outer reaches of the solar system for eons, or perhaps to be captured eventually by the growing gas giants that are simultaneously condensing in the more distant regions of the nebular disk. Other fragments receive just enough energy to enter highly elliptical orbits that will eventually bring them back into the vicinity of the proto-Earth, though perhaps not for thousands or tens of thousands of years, creating a complex population of debris that continues to interact with the growing planet across extended timescales. These hit-and-run collisions contribute their own layer of subtle irony to the planetary formation process in order to successfully build a stable, coherent planet capable of retaining a permanent atmosphere and eventually supporting life. The proto-Earth must survive countless encounters that possess the potential to destroy it entirely, to fragment it back into constituent pieces and scatter those pieces across interplanetary space. The difference between construction and destruction often depends on factors so small they approach the limits of measurement. Slight variations in impact angle measured in degrees, differences in approach velocity measured in meters per second, variations in the internal density and structural integrity of the colliding objects that depend on the precise sequence of their own formation histories. The growing proto-Earth develops an increasingly complex internal structure as the accumulating mass creates gravitational fields strong enough to overcome the structural strength of rock and metal. Heavier materials, particularly iron and nickel that will eventually form the planet's core, begin to sink toward the center under the relentless pull of gravity, while lighter silicate materials rich in aluminum, silicon, and oxygen float toward the surface like oil separating from water. Though the process occurs in solid and semi-solid materials rather than fluids, and takes millions of years to approach anything resembling completion, this process, which planetary scientists call differentiation, proceeds with the same geological patience that characterizes all aspects of planetary formation, establishing the basic core mantle crust structure that will eventually define Earth's internal architecture and drive the tectonic processes that reshape its surface. The energy released by this gravitational settling, as dense materials sink through lighter ones and potential energy converts to heat, adds significantly to the thermal budget of the forming planet, contributing to an internal environment that grows steadily warmer with each passing geological epoch. The heat generated by differentiation combines with the thermal energy from ongoing impacts to create temperature gradients within the proto-Earth that would be lethal to any conceivable form of life, though life remains an impossibility for numerous other reasons related to the absence of stable surface conditions, liquid water, and the complex chemistry that will eventually emerge from more stable environmental conditions. The interior temperatures begin to approach the melting points of common rock-forming minerals, creating zones of partial melting where solid crystals coexist with pockets of liquid magma, establishing the conditions that will eventually lead to volcanic activity and the complex geochemical processes that will reshape the planet's surface composition. Throughout this extended period of violent construction that spans tens of millions of years, the proto-Earth maintains no stable surface, no consistent atmospheric composition, no recognizable geography that would persist long enough to be mapped or studied. Its appearance changes constantly as new impacts add material and rearrange the distribution of mass, as differentiation drives internal reorganization, as the heat generated by these processes creates localized zones of melting and chemical alteration. The boundary between solid surface and space remains fluid and constantly redefined by the latest collision or the most recent episode of internal reorganization. Any hypothetical observer positioned at a safe distance from this dynamic construction site would see not a planet in any familiar sense, but rather a constantly changing aggregate of cosmic debris held together by its own gravity and shaped by the relentless accumulation of kinetic energy from countless impacts. The surface glows with the dull red heat of repeated collisions, punctuated by the brilliant flashes of new impacts that temporarily illuminate the surrounding space with light bright enough to be visible across interplanetary distances. The proto-Earth resembles less a solid world than a gravitational gathering point for cosmic debris, a three-dimensional intersection of orbital mechanics where matter accumulates according to the patient mathematics of celestial mechanics. The timescales involved in these formative processes stretch beyond easy human comprehension, requiring a fundamental shift in temporal perspective to appreciate their true character. individual collisions might be separated by thousands or tens of thousands of years, intervals long enough for entire civilizations to rise and fall, for species to evolve and go extinct, for continents to shift position on a modern Earth. Yet from the perspective of planetary formation, these events occur in rapid succession, like raindrops falling during a summer storm, each impact building on the accumulated effects of all previous encounters to drive the proto-Earth toward the critical mass and internal temperature necessary for the next phase of its development. The proto-Earth's mass doubles, then doubles again, then continues growing in a progression that appears exponential when viewed across millions of years, but feels glacially slow when measured against the lifetime of any individual object involved in the accretion process. This mathematical progression follows the laws of gravitational dynamics, where larger objects capture material from increasingly large volumes of space, accelerating their own growth in a positive feedback loop that will eventually dominate the local environment and sweep up most of the available solid material within the orbit that will someday be called Earth's zone in the solar system. The growing proto-Earth begins to exert its gravitational influence across an ever-widening sphere of space, fundamentally altering the orbital dynamics of the entire inner solar system through what amounts to cosmic-scale environmental engineering that operates according to the patient mathematics of celestial mechanics. Objects that once followed stable, predictable elliptical orbits around the condensing sun now find their trajectories gradually perturbed by the increasing mass concentration that will eventually become our planet. These gravitational perturbations accumulate over thousands of orbital periods, causing small asteroids and larger protoplanetary fragments to spiral slowly inward toward collision courses that were not predetermined by the original conditions of the solar nebula, but emerge from the complex interplay between growing planetary masses and the fundamental laws of orbital mechanics. The scientific mystery embedded in this phase of planetary formation involves the precise mechanisms by which a growing planet manages to avoid disrupting its own accretion process through gravitational interference. Theoretical models suggest that as the proto-Earth approaches approximately 10% of its final mass, roughly equivalent to the mass of modern Mars, its gravitational field becomes strong enough to significantly alter the orbital characteristics of nearby objects, potentially scattering away the very material it needs to continue growing. This represents a delicate balance between gravitational capture and gravitational disruption, a cosmic tightrope walk where success depends on maintaining growth rates that fall within narrow mathematical boundaries defined by orbital resonances and the competing gravitational influences of other growing planets. Current understanding of this process remains frustratingly incomplete, limited by the impossibility of directly observing planetary formation in action, and the extraordinary computational complexity required to model the simultaneous gravitational interactions of millions of individual objects across timescales spanning millions of years. The most sophisticated computer simulations can follow the evolution of perhaps a few thousand representative particles for a few million simulated years, a sample size and duration that captures only the broadest outlines of processes that actually involve countless billions of objects interacting across tens of millions of years of real time. The heat budget of the proto-Earth continues to grow with each collision, creating internal temperatures that begin to approach and occasionally exceed the melting points of common rock-forming minerals such as olivine, pyroxene, and feldspar. This thermal evolution marks another crucial threshold in planetary development, the point where the growing world transitions from an essentially solid aggregate of cosmic debris to a partially molten body capable of supporting the complex internal dynamics that will eventually drive plate tectonics, volcanism, and the geochemical processes that will create and maintain the conditions necessary for life. The first pockets of liquid rock begin to form deep within the proto-Earth's interior, where the combination of impact heating, gravitational compression, and the heat released by ongoing differentiation creates temperatures exceeding 200 degrees Celsius. These initial magma chambers exist as small, isolated pools of molten material surrounded by solid rock that still retains the primitive composition and structure inherited from the original nebular condensation process. The liquid rock possesses a lower density than the surrounding solid material, creating buoyancy forces that drive it slowly upward toward the surface through cracks and fractures in the overlying solid layers. The irony of this thermal evolution lies in its reversal of the normal relationship between temperature and depth that will characterize the mature Earth. In today's world, temperatures generally increase with depth according to the geothermal gradient, reaching their maximum values at the core mantle boundary, some 2,900 kilometers below the surface. But during the Hadean formation period, the highest temperatures often occur near the surface, where the most recent impacts have deposited their kinetic energy, while the deep interior remains relatively cool, composed of materials that have not yet experienced sufficient compression and heating to reach their melting points. This temperature inversion creates convection patterns unlike anything that will exist during later periods of Earth's history. Hot surface materials, heated to glowing temperatures by impact energy, gradually sink into the cooler interior, while cooler deep materials rise toward the increasingly hot surface in a complex three-dimensional circulation pattern that operates across timescales measured in millions of years. These convection currents drive the first large-scale mixing processes within the proto-Earth, beginning the homogenization of chemical composition that will eventually create the differentiated structure of core, mantle, and crust that defines the modern planet's internal architecture. The surface of the proto-Earth during this period bears no resemblance to any landscape that will ever exist on the mature planet. Instead of solid ground covered by soil and vegetation, or even bare rock sculpted by erosion and tectonic forces, the surface consists of a constantly changing mosaic of impact craters in various stages of formation and modification, separated by regions of cooling lava flows and zones of upwelling molten material. The temperature varies dramatically both spatially and temporally, ranging from the searing heat of fresh impact sites, where surface temperatures can exceed 2,000 degrees Celsius, to relatively cool areas that have had time to radiate their energy into space and approach the freezing point of water. The atmospheric composition during this period reflects the ongoing violence of planetary construction. Each major impact vaporizes significant quantities of surface rock, adding silicate vapor to the thin gaseous envelope surrounding the proto-Earth. This creates an atmosphere composed primarily of rock vapor, a concept so alien to modern experience that it requires considerable imagination to visualize. Silicon dioxide, aluminum oxide, and magnesium oxide, substances that exist as solid crystals under normal terrestrial conditions, float as invisible gases in the tenuous atmosphere of the forming planet, creating conditions that will not be duplicated anywhere in the solar system once planetary formation concludes. The pressure of this rock vapor atmosphere remains extremely low by terrestrial standards, perhaps 1,000th the pressure of modern sea level air, yet it represents a significant increase over the near vacuum conditions that characterize the earlier stages of accretion. This atmospheric thickening creates the first primitive greenhouse effect in Earth's history, as the rock vapor absorbs and re-radiates thermal infrared radiation more efficiently than the previous near-vacuum conditions. Beginning the complex feedback processes between surface temperature, atmospheric composition, and planetary energy balance that will eventually regulate Earth's climate, the magnetic field of the proto-Earth, if it exists at all during this period, remains weak and intermittent, generated by the chaotic convection of partially molten metallic material in the forming core rather than the organized circulation patterns that will eventually create the stable dipolar field that protects modern Earth from solar radiation. This magnetic weakness leaves the thin atmosphere vulnerable to erosion by the solar wind, the stream of charged particles flowing outward from the young sun, which strips away atmospheric gases at rates much higher than will be tolerated once a stronger magnetic field develops. The day length during this period fluctuates wildly as large impacts transfer angular momentum to or remove it from the rotating proto-Earth. Some collisions, particularly those that strike the planet at oblique angles, can significantly speed up or slow down the rotation rate, causing the length of the day to vary by hours or even days from one impact to the next. This rotational instability contributes to atmospheric and surface dynamics unlike anything that will characterize later periods of Earth's history, creating weather patterns and circulation systems that operate under constantly changing boundary conditions. The growing planet sweeps up material from an increasingly large volume of space as its gravitational cross-section expands, accelerating the accretion process in a positive feedback loop that will eventually lead to runaway growth once a critical mass threshold is reached. This gravitational focusing effect means that the rate of mass accumulation increases exponentially rather than linearly, transforming the proto-Earth from a minor player in the solar system's gravitational dynamics to an increasingly dominant force that will eventually capture or scatter most of the solid material within its orbital zone. The mathematical inevitability of runaway accretion begins to assert itself as the proto-Earth approaches approximately 1/4 of its final mass, crossing a threshold where gravitational focusing becomes so efficient that the planet begins to dominate the orbital dynamics of everything within its expanding sphere of influence. Objects that previously followed stable trajectories around the young sun now find themselves drawn inexorably toward collision courses with the growing world, their orbital energy slowly bleeding away through gravitational interactions that operate like cosmic friction, invisible but inexorable. This represents the beginning of the end for the chaotic, debris-filled environment that has characterized the inner solar system since the collapse of the original solar nebula, as the proto-Earth transforms from merely another large object among many into the gravitational overlord of its orbital neighborhood. The process unfolds with the same patient persistence that marks all aspects of planetary formation. Yet the consequences accelerate dramatically as the growing planet's gravitational reach extends farther into space. What began as occasional random collisions between objects following independent orbits evolves into systematic gravitational harvesting, where the proto-Earth actively captures material from volumes of space hundreds of times larger than its physical cross-section. The mathematical beauty of this transition lies in its self-reinforcing character. Each successful capture adds mass that increases gravitational attraction, which enables more efficient capture of additional material, which adds more mass, creating an exponential growth curve that will transform the inner solar system from a realm of countless independent objects into a much simpler arrangement of widely separated planets. The heat generated by this accelerating bombardment begins to fundamentally alter the physical state of the proto-Earth's interior, creating conditions that have no analogue in the modern solar system and will never be duplicated once planetary formation concludes. The accumulated thermal energy from millions of impacts drives internal temperatures well above the melting points of most common rock-forming minerals, creating vast zones of partially molten material that extend from the surface down to depths of several hundred kilometers. This represents the birth of what planetary scientists call a magma ocean, though the term ocean implies a stability and permanence that this violent, constantly churning environment completely lacks. The magma ocean exists in a state of continuous turbulent convection, driven by the constant input of impact energy from the surface and the ongoing release of gravitational potential energy as denser materials sink toward the center and lighter materials rise toward the surface. The circulation patterns within this molten realm operate on timescales ranging from days for near-surface flows to millions of years for deep convection cells that extend through the entire thickness of the partially molten zone. These convection currents create the first large-scale chemical mixing processes in Earth's history, beginning the homogenization and differentiation that will eventually separate the planet's interior into the distinct chemical and physical layers that characterize its modern structure. The scientific mystery that haunts this period involves the precise mechanisms by which heat escapes from the proto-Earth's interior to prevent complete melting of the entire planetary mass. Theoretical calculations suggest that if all the kinetic energy from major impacts were retained within the planet, the internal temperatures would rise high enough to completely vaporize even the most refractory materials, transforming the entire proto-Earth into an expanding cloud of rock vapor that would dissipate into space rather than condensing into a solid world. Yet somehow, through processes that remain poorly understood, the growing planet manages to radiate away enough thermal energy to maintain at least some solid structure. Even as impact rates reach their maximum intensity, current models propose that the key lies in the efficiency of thermal radiation from the glowing surface, which operates according to the Stefan-Boltzmann law and increases proportionally to the fourth power of absolute temperature. As impact heating drives surface temperatures higher, the rate of energy lost to space increases dramatically, eventually reaching equilibrium with the rate of energy input from ongoing bombardment. This thermal balance represents another delicate tightrope walk in planetary formation, where success depends on maintaining impact rates high enough to drive continued accretion, but not so high that they completely overwhelm the planet's ability to dissipate the resulting heat. The surface temperature during the peak of this bombardment period reaches levels that would vaporize most materials instantly, creating a perpetual shroud of rock vapor that obscures the solid surface beneath like a planetary-scale industrial accident. Silicon dioxide, magnesium oxide, iron oxide, and aluminum oxide float as gases in an atmosphere that bears no resemblance to any modern planetary environment, creating optical properties that would make the proto-Earth appear as a glowing red-orange beacon visible across interplanetary distances. The atmospheric pressure, while still low by terrestrial standards, increases dramatically as impact vaporization adds material faster than thermal escape can remove it, creating the first substantial gaseous envelope in Earth's history. This rock vapor atmosphere possesses greenhouse properties far more extreme than anything caused by carbon dioxide or water vapor in modern terrestrial climates. The complex molecular structure of silicate gases creates absorption bands throughout the infrared spectrum, trapping thermal radiation with an efficiency that drives surface temperatures even higher than the already extreme levels created by direct impact heating. This atmospheric greenhouse effect represents the first example of climate feedback in Earth's history, demonstrating how changes in atmospheric composition can amplify or moderate the effects of external energy sources. The magnetic field generated by the proto-Earth during this period remains chaotic and variable, reflecting the turbulent convection patterns in the partially molten metallic core that has begun to differentiate from the surrounding silicate materials. Unlike the stable dipolar field that will eventually protect Earth's atmosphere from solar wind erosion, this early magnetic field consists of multiple, rapidly changing poles that provide little protection against charged particle bombardment from space. The combination of weak magnetic shielding and extreme surface temperatures creates atmospheric loss rates thousands of times higher than anything that will characterize later periods of Earth's history. The rotational dynamics of the proto-Earth during this bombardment phase remain highly unstable, as large impacts continue to transfer angular momentum in random directions, causing the rotation rate and axis orientation to fluctuate wildly over timescales ranging from individual impacts to thousands of years. Some theoretical models suggest that particularly massive collisions during this period might have been capable of stopping the planet's rotation entirely, or even reversing its direction, creating episodes where the sun would rise in the west and set in the east. If anyone had been present to observe such phenomena, and if the surface conditions had permitted the existence of recognizable sunrise and sunset, the chemical composition of the magma ocean evolves continuously as ongoing impacts add material with varying elemental abundances, while fractional crystallization and gravitational settling remove different components at different rates. The earlier stages of differentiation begin during this period, as the densest materials, particularly metallic iron and nickel, sink toward the center to form the first recognizable core, while the lightest materials, particularly those rich in aluminum and silicon, float toward the surface to begin the process of crustal formation. This chemical separation occurs against the background of constant mixing caused by impact-driven convection, creating a dynamic equilibrium between differentiation and homogenization that will persist until impact rates finally decline enough to allow stable layering to develop. The timescales involved in this peak bombardment period compress the most violent aspects of planetary formation into a relatively brief interval, perhaps spanning only a few million years despite the geological context that surrounds it. During this compressed time frame, the proto-Earth experiences more large impacts than it will encounter during all the remaining billions of years of its existence, creating surface conditions so extreme that they serve as a baseline for comparison when planetary scientists discuss the most hostile environments anywhere in the solar system. The irony embedded in this violence is that these same extreme conditions drive the chemical and physical processes that will eventually create the stable, differentiated planet capable of supporting the complex geology and atmospheric dynamics that will make life possible. The proto-Earth's gravitational dominance over its orbital zone reaches a mathematical tipping point where the capture efficiency approaches unity, meaning that virtually every solid object within a vast spherical volume